All right, so today we'll finish up the treatment of threads and concurrency, I think. Talk a little bit about some other synchronization operations, barriers, condition variables, and then a brief foray into how we implement these things when there's weights involved. So far we kind of looked at how to implement a lock and how to implement a weight lock in the kernel, but how do you do a weight lock in user space? That's a lot more complicated, it turns out. And then what was there? I forget. I had something important more we were going to talk about. Oh yeah, signals. So signals have some strange interactions with synchronization, and the next homework will also be signals. Not so much with the synchronization interaction, but basically we want to be able to kill a process by hitting Control-C and such. Right? And that'll take a little bit of surgery in the OS. Right. Before that, any questions on the homework? Just due on Thursday. There are a couple people in office hours. Who's finished? 2? All right. It seems like there's more that are at least close to it. Maybe one thing that came up in office hours that I thought was pretty interesting. I discovered, at least in my solution, there's a small bug. The stack that you allocate on thread create, really one ought to be freeing that on thread join. Right? It does get freed anyway when the process exits, but in order to be really proper, we should free it on thread join. And so the question then is, how do you get the stack pointer? Like, how do you know what to pass to free? Well, we created in the thread create, but then it's not available on thread join. It's not like you pass in the stack pointer on thread join. You just say join that thread. So I think there's 2 ways that you can do it. I think the easiest in x86 would be to have the thread join system call return whatever pointer you passed in with thread create. So just store it in your struct proc. Like, here's the user stack. That would work. If that's returned, then after thread join, the thread is already dead. So now we can safely just free whatever came back. Or maybe we need to add a little bit to it because we probably put the return address on the stack, right? So maybe we have to add 8 bytes, or add 8 to the stack pointer that came back, and then free that. Another way, which I think is what pthreads does, is you have they have a pthread type. And so when you do a thread create, you get a struct back, and that is a user space struct that tracks a few things. I suspect it tracks the process ID, or the thread ID, the one, so you can tell the kernel things. Probably then tracks the stack, and perhaps some thread local other attributes, like how it should be scheduled and things like that. So that's another way, but we're not doing that we don't have that in the homework setup, and you certainly don't need to free the stack to the user stack, that is, to get the full points. I would be very careful about the kernel stacks. Right? There's when a thread dies, or when a thread is told to die, it eventually goes and kills itself. You can't kill the thread from a distance. The only thread that can safely set it to a different state is the thread itself. Right? You can set it to, if it's sleeping, another thread can set it to runnable. That's fine. I think the scheduler maybe sets it to running. But when it's running, if you just go and set it to unused, or to zombie, or to whatever you want while it's running, that's just not okay. Right? It needs to decide that I am no longer running. Right? So what I used was the killed flag in the struct proc. So basically, when I want the process to die, there was never a situation where I want just one thread to die. So if I want the process to go and die, I set the killed flag. Every thread eventually discovers that the killed flag is set, so it calls exit. course, you can't have multiple threads running the exit code at the same time, because that's weird. I mean, it's freeing the process multiple times and all of the file descriptors and things. So they have to agree on one of them doing it. But basically, that makes it pretty easy. There isn't a whole lot of code you need to change in order to make it work right. Right. So on exit, I just set the killed flag then to 1, and then everyone else goes and kills themselves. And when they're all done with that, then I continue and free up the process. That was my solution. Okay. So let's talk a little bit about some other synchronization operations. There's a couple. We've talked mostly about locks so far, but there's a couple that you should be aware of if you aren't already. It doesn't hurt to get a brief refresher on it. One is called a barrier. The other one is, okay, so we had locks, a barrier, and then there's condition variable. And then there's something called a semaphore. Oh. And that's more of an abstract synchronization op. This is not something people generally use. Sometimes they are provided, like sometimes there's something called a semaphore, perhaps in the context of a file system or something. Generally, semaphores are used in textbooks and in problem sets because they make for kind of cute homework problems, as in something you can write in a few lines on a piece of paper and makes for a good exam question and so on. But it doesn't make much sense in terms of how you implement it on the machine, how to use it. So you wouldn't find it in any very concrete use generally. So semaphores are this thing where you have a number that goes up and down, and then when it's 0, then the semaphore is free, and you can use it for implementing all these other synchronization operations, but there's no point in using them for that. It just gets slower if you have this extra layer of indirection. All right, so with the locks, basically we know we have, it's locked or it's unlocked. That's it. For a barrier, there's a capacity or something, like a size. It's a size set at initialization. So when you first make your barrier, you say this is a barrier of size 3. And then you can wait for the barrier. That's the only operation. Maybe to be complete, that's the state. And then we have acquire and release. I prefer those terms to lock and unlock, just because so many uses of the same word. Okay, so a barrier has only these two things: the state that you set the initialization, the size that you set the initialization, and then a wait function. And the wait function blocks until enough threads are waiting, enough being the size. So this could be very handy. For example, if you have a main thread that starts a bunch of client threads, but it doesn't want to do anything until all the client threads have spun up and started, done all their initialization and so on. So there you would say, oh, I'm starting n threads, so I'll make a barrier for n plus 1, size n plus 1, and then I'll wait on the barrier. And all the clients, they basically do all their work until they're ready, and then they wait on the barrier. So now all the clients and the server are all together done, kind of finished with initialization, and then suddenly they go. So this is very handy, just to make sure everyone's ready before you proceed. If you've taken 361, sometimes we have this elevator homework, and there's some very good uses for barriers in terms of not getting crushed by elevator doors and that sort of thing. So barriers are handy to avoid getting started too early, but one thing to keep in mind is that there's no guarantee as far as when you will continue. Like, we know that you will not continue before everyone has come to the barrier. But after that, all bets are off. So it's not like they all start at the same time. They just start after a certain time. It's important to note. We often use it to do when we run various concurrency tests on our research projects. Then we start a thread running on each of the various cores, and then if you don't use a barrier, then it might be that one core finishes before even another core has gotten started. If you do it that way, now you don't really get any concurrency. It's just like first run that one and then run this one and run this one, and all the cache coherency and such. All those problems don't appear because they're all running in series. So the barriers kind of help to make them start at the same time, but there's no guarantee. So in order to really guarantee it, that things are working this way, we also run a long experiment. So if you were to say set a barrier and then try to make all the threads do one I++ one after another, you may not see any sort of consistency violation. You have 10 threads, you probably get 10 increments. It's all fine, even though the barrier said start at the same time. But if you do each one of them a million times, probably there's going to be some overlap, and now you can see your problems. Okay, so barriers are very easy to use. And I think generally barriers are reentrant, so once everyone has waited, once you kind of fall through the barrier, then you can restart again. You don't have to initialize it, you just start waiting for it again. There are some, implementing a barrier is not trivial, because there's lots of strange corner cases, but I don't think we need to worry about that here. Things like what happens if more than k threads are waiting for come in and wait for the barrier at the same time. Now what's the state and that sort of thing. Okay, so condition variables are not what they sound like. What's very strange about a condition variable is that there's no condition in there. So it's more of a, and actually I can't think of a good I cannot think of a good other name for it. Maybe that's why it's called a condition variable. No one else could think of a good name either. Either way, a condition variable has no state, really. It has two operations. There's a wait and there's a notify. So here the general idea, or maybe I should say blocks until size threads called wait. Okay, so with a condition variable, you can have any number of threads called wait on the condition variable. Blocks until notify, or randomly returns. So you call wait and then sometime later you wake up. That's all a condition variable does, except another thread can call notify. Actually, let me take that back. There's one more thing that happens. So there's also a lock. This is very important. Maybe we should go like this: con variable lock, because this is C after all. There's no methods on objects. So let's do it this way. Okay, so you call wait. This is a very important point. It releases this lock. Blocks until and then returns with lock held again. All right. So if you call notify, then everyone who's waiting for the condition variable will wake up. So this one here is pretty important. So we're holding a lock, we're working on some data structure, and we're guaranteed that when we wake up, so we call wait here, we lose the lock for a moment, but we're guaranteed that by the time we wake up, we receive the lock back again. So this is handy if you have multiple waiters and they're all in this critical section. Say they're waiting on they're holding a p-table lock because they want to modify something, or they're waiting for someone to wake up or whatever. Now only one at a time will enter the critical section here, right? They are all waiting. They're wanting to hold the lock. They all get woken up, but only one of them at a time will run because they're guaranteed that they will hold the lock when they come back from this function. You got a question?
Yeah, regarding that, I mean, if everyone was notified at the same time, then how would they'd have to sleep again because the lock would only go out to one thing.
Yeah, exactly. So so they will not return at the same time. They're woken up at the same time. Trying to think of how we would implement it in XV6. We don't have user space condition variables in XV6. We really ought to be waking up all of them. So I guess, yeah, so it turns into, so first you're waiting for the condition variable. You're in a sort of a cond wait state. Then when you get notified, sometimes this is called signal. I should use both. It's the same thing. So then when we signal the condition variable, all of the threads that were in the cond wait state, they now turn into a lock wait state. Right? They're trying to acquire that lock again, but they're kind of ready to get it. Right? That's how you'd have to implement it. Yeah, so this is sort of necessary because what would we do otherwise? Well, we could release the lock, and then we could just wait for the condition variable and try to acquire the lock, but you'd get a lot of weird effects. Because now you have all these threads waking up, and then they go back to sleep again, and probably by the time they get there, the condition isn't true anymore. And this is just a convenient way to have it, to make it work, I think. Okay, but there's a couple of very important points here. I think, well, maybe there's just the one. This one here. Actually, I guess this is randomly returns and returns with a lock held again. So the fact that it returns with lock held again means that if there's more than one waiting, the data structure that you were in a critical section holding the lock for this data structure, that data structure probably will have changed by the time you come back from the wait. So even if the condition was true for a while, someone else was waiting, they got it first, they grabbed whatever you were waiting for, and now you can't have it anymore. And so we always have to check for this condition to be true. So there's two reasons for it. One is this fact that there could be more than one competing for it, and only one of them will get it. And the other one is we can get random or spurious wake-ups out of condition variables. So the way we have to treat condition variables, always, we have to write while my condition isn't true, sleep. Oh. Right, so I guess it would usually go like this. So here what happens is we're checking, and my condition could be anything you want. Like while the number of processes is greater than 4, you know. So while we have more than 4 processes, keep waiting. And this convar here has nothing to do with the condition, right? There's nothing inside of the condition variable that says anything about the number of threads. It's just a thing you can wait on, and get woken up by. So I'm checking here while all the number of processes is greater than 4, just wait. And anytime I could be woken up. But at least when I'm woken up, I'm guaranteed I'm still holding the lock. Maybe the p-table lock here. I need it in order to check the condition, right? I'm not allowed to check the number of processes unless I'm holding the lock. So now I'm holding the lock. I suppose in here I could maybe release it and then acquire it after. Maybe that could work, but it's very inconvenient. This is a faster and more convenient setup. All right, so at some point, I will have woken up a bunch of times. At some point, the condition becomes true, and then I go through and I create a new process, let's say, because now there's only 4 processes, so I can make another one for whatever reason, and then I release the lock. So this is the general way that we use condition variables, and it's always unsafe to not have this while loop. Make sure if you write a condition, anything with a condition wait, you have a while loop. The same is true for your sleep in XV6. Sleep is really a condition variable, sort of a primitive implementation of a condition variable. There we're sleep, let's see. I think are we passing in a lock in that one, or is it always the p-table lock? I think it's a p-table lock. Huh?
They're always passing in a lock, but it's always the
I see, okay. Let's find a sleep here just to make sure. Here it is. Okay, yeah, so we are passing in a lock. Right, so it's the same deal. So this is the condition variable if you want. It's not really, there's no difference between a channel and a variable really. What's interesting about this here is you can actually get correct operation if you always pass in a 0 for channel and you always use a 0 for notify. Right? Then anytime you notify, or is it signal? Wake up, yeah. So anytime you call wake up on anything, if you call it with a 0 always, you will wake up everyone who was waiting for anything. And that's fine, because all the code anyway has to be checking that condition to see if it was for them, if this was a correct wake up. So why don't we always do it that way?
It's a hassle, right? I mean, everything wakes up by one.
Well, they're all waking up anyway. I mean, we already have the code there. What's the hassle?
Extra cycles.
Yeah, it's not very efficient. So, and that's the only reason really. But you could end up having thousands of threads all waiting for a lock or something, and now every time we send a signal here, now suddenly all of those guys keep waking up and they have to check something and then they go back to sleep. It's not good. So that's the only reason we have the condition variable really. Otherwise we could just have a sleep with nothing and then wake everyone up who's sleeping. Okay, so here we're calling, where are we releasing? Ah, here we are. So in order to call the scheduler, you have to have the p-table lock. But we know the scheduler will then pass the lock on to, well, the lock actually goes into the scheduler, so to speak, and the scheduler will eventually hand control over to whoever was waiting, and then that one will release it, just like here. But yeah, we do release the lock that's passed in, and then we acquire the lock in the end that was passed in again. So basically, we probably could safely do this in user space just as well, or in sort of where we are doing our condition variable management. But there's some nice optimizations you can do, which we don't do here, but there's nice optimizations you can do by passing in the lock to the wait. All right. So that's condition variables. The signaling part is really simple. It's just like the wake up. We loop through, everyone is waiting for a channel, or in the case of a condition variable, we'll have a queue of people waiting for the condition variable, and we just wake them all up. All right. Any questions on this stuff? No.
Is the condition variable normally something simple like an integer in the user space, or how does it look like?
You mean what is the struct?
Yeah.
I would think it's a linked list, right? Where every waiter would add itself, but I don't know. Yeah. So in addition to that, probably, well, actually we'll get to the user space implementation in a moment here. So. All right, so those are really the remaining synchronization operations that we need to worry about. Can't think of anything else. Can anyone else think of another synchronization operation that seems to show up occasionally? Yeah. I mean, there's specialized versions of locks, like a reader-writer lock, or the try locks and such. But basically, locks, condition variables, and barriers, we're probably good. Okay, so yeah, and if you're interested in semaphores, just look it up in an OS book. It's a popular theoretical concept, mostly. Right. So the question for today, I guess the main question for today perhaps, is how do we implement all this waiting in user space? So a spin lock is really easy to implement in user space. You just have your thread over and over try a compare and exchange. And at some point the lock, the variable is a 0, it's unlocked, and it becomes a 1. So if you let's see if we remember this. So compare and exchange, it's an atomic. Goes something like address to a variable, old value, or maybe, yeah, let's go like that, and new value. Actually, let's call it expected value. So now if variable, so all of this is done atomically in here, it's done in hardware, right? So if the value of the variable equals the expected value, set variable equals new value. Otherwise we don't really do anything. Okay, maybe I'll go like this. Return expected value. And otherwise we return. Okay, there it is. So all of this is executed atomically. So what we can do is we say if the expected value is free, right? Lock is not acquired. Here's the lock. If the lock is not acquired, set it to locked. That's atomic compare and exchange. So in that case, right? So here, if it was not locked, all atomically, right? If it's free, then set it to locked and return it was free. Otherwise, we return it was locked, right? That's the old value. In both cases, we're actually returning the old value. It's just that I would have to store the old value first somewhere if I was to have only one return statement. Okay, so using this, we can just do a spin lock as compare compare and exchange, lock, locked, unlocked, locked. There's a spin lock. Right, so keep trying to lock this lock as long as this is a little weird. Sorry, I don't actually know the order of these things. Could well be that it works, but it's much better that way. So as long as it wasn't unlocked when we entered, that means we didn't get it. It was locked, so we have to keep trying. So in user space, that's how you would implement it. That's great, except if we're using multiple threads on a single core, now we have a bit of an issue. Because now we're spinning until a timer interrupt goes off, and then it'll change to another thread that may or may not hold the lock. It'll run that thread for a while, spinning, probably, if that one also is trying to acquire the lock, right? And at some point, much later, we'll get to the thread that actually is holding the lock, and it'll complete the critical section and unlock the lock, right? Let's see. No. There. Acquire. And release goes lock equals unlocked. Okay, so what we want is to run the thread that's holding the lock and not run the other ones, right? So how do we do that? What's that? Yield. Okay, that's pretty good. So let's try it. Like that? I think this is a dramatic improvement already. But unfortunately, that thread that is holding the lock, it got swapped out because it used a lot of the CPU. Right? That's usually like, at least with a completely fair scheduler, right? You use too much CPU, you get swapped out, someone else gets to run, and whoever's trying to acquire the lock, well, they didn't use a whole lot of CPU, so they might very well run again. They yield it and they ask the scheduler, well, it's your turn, go ahead, right? Or if not, it's the other thread that also wants the lock but isn't holding the lock. So now you have all these threads going back and forth, yielding the CPU. I don't know that it's better. Maybe it's a little bit better. But at least if the CFS works the way we have talked about it, as in you only sort of pay for the amount of CPU you used, then you will use the same amount of CPU here before the thread that holds the lock gets to run. So it's not really doing it. Okay, so if the lock knows who is holding it, then we can do some sort of prioritization or something, yeah. But we already have some interesting information here. We know that we're not holding it and we want it. That ought to be enough. That means we should not be running.
What's stopping us from just sleeping?
Okay, let's try that. Well, we should have some parameter, I suppose.
Yeah.
Like what? Are we sleeping for a set amount of time, like 1 second? Let's sleep for something else. Well, maybe we don't call it sleep because the sleep system call has a time sort of. but let's call it weight. Right? Actually, weight is this other thing. So let's call it futex weight, because that's what it's actually called. Futex is for fast user space mutex. And it's fast because it doesn't spin, I suppose. All right. So, but we still have to figure out what futex weight does and what parameters it's taking. So, what is it we're waiting for?
We're waiting for the lock to be free.
Okay. So we're waiting for the lock. And we're waiting until it's unlocked. Is it? Okay. Pretty good.
It has the same issue where I think there's a bunch of futex wait calls in different threads, and they're all waiting at the same time. So they might all be woken up again at the same time.
Very good.
But that'll only happen once, then they'll go back to sleep after they.
Yeah, but then that'll happen every single time the lock is released, because everyone else is waiting for that lock.
Yeah, so we're in pretty good shape. I think every thread here goes to futex wait. It's not spinning. Presumably there's something we need to do about the release though. Because so far at least, these threads are not running anymore, so how can they wake up? So we need something here. I guess we'll say futex wake up lock. Okay, so this is a little bit unfortunate, I think, because release used to be so efficient, and now we're doing a system call all the time. But there you are. Let's live with that. And maybe there's some optimizations we can think of later. But all right. So so the problem that you pointed out is that we do a lot of work for every acquisition. So all the threads come in and wait until they get signal. So for every release, everyone wakes up. It'd be better if only one of them wakes up.
We could put them on a queue.
Put them on a queue.
First come, first served system.
Let's see. Probably. Okay, so we could try that. So now the semantics are on futex wait, you wait until you get woken up, but wake up only wakes up the first one in the queue associated with the lock. So this is getting a little bit complicated because now the kernel needs to be accessing the lock data structures. Before this, we were only looking at the lock value, but now there's I don't know if I like this, because now the kernel needs to allocate memory that goes in a user space data structure, and the kernel certainly doesn't have access to malloc. It gets a little iffy, but let's say we could do it. You know, we could have an out of band data structure that the kernel manages on its own. So we only wake up whoever's first in the queue. Any concerns about this? Other than the memory management headaches? I think it's much better than it used to be, because now at least only one thread comes back out. But it's still not clear that this thread that came out of the futex wait actually gets the lock. Because there could be some other thread that is just running, it wasn't sleeping. So that seems a little dubious. Like now you wake up this thread and then it comes back out and there's nothing there for it. So it's got to go back in. I think we can do a little bit better.
you're waiting on the lock and only one thread is unlocked, why do you need to have a while loop anyway?
Waiting.
Because
Oh yeah, if you could trust it.
yeah.
Yeah, but for any of these wait things, we can't trust it. There's always spurious wake-ups, and it has to do with signals mostly. Maybe we'll see it a little bit later, but yeah. So this is just like a condition variable, really, in that sense. So here's my proposal. We say what value we want it to have as well. So we don't come back out of user space until the lock is set to locked, and it's held by us. So now we can imagine how we would implement this, I think. Actually, this might be a pretty cool homework, a futex system call. You can imagine how to implement this thing. Right, we would just have every thread that calls futex wait, first see, when it gets into the system calls, see if it is still unlocked. See if it's still locked. And if it is, then start waiting for this channel. And then try to acquire it in the loop, try to acquire it, set it to locked, and then maybe return to user space after that. I think we have almost everything that we need in the kernel. Okay, so it's actually it's relatively complicated to get this to work right. I don't think that this one is quite there. Let's see. There was this beautiful document by what's his name? Let's see if I can find it. One of the main programmers behind Linux. What's his name? Ulrich Draper is his name. It's called Futexes Are Tricky. This is a great little paper to read if you're interested in this sort of thing. There was just one example I thought we'd take a look at to see how they do it. There's several steps like, oh, why doesn't this work, and so on. But let's take a look at one that makes sense. That isn't particularly broken, but maybe it's not the most efficient. So here, a lock can have three states. It can be unlocked, it can be locked without anyone else waiting, or there's one or more threads already waiting for the lock. And here's the implementation. Look at that. I'm confused. Shouldn't the wait have a... Okay, so perhaps in this one they don't actually set it. So here we're waiting while the variable remains at 2. Okay, so this is the interface here. Maybe I told you a lie there. Perhaps this setting, well, it ought to add some efficiency. Oh, okay. I'll think about like acquiring the lock in kernel before returning to user space, and maybe post something on Piazza. Okay, so here's our acquire function. So basically, we want to make it pretty efficient. If there's only one thread holding it, and I think we let's see how this goes. All right, so if the lock is free, then we try to take it. All right, so if we didn't get it, now if there's at least one thread already waiting in the kernel, then we have to do a futex wait too. So this is to have some sort of fairness, I think. If we try to grab it, if there's someone waiting in the kernel and we just try to grab it, this would be maybe be a bit of a fairness issue. I'm not sure. Let's see. So here, if there's already someone waiting, well, then we go and wait. Otherwise, you see, if there was only one thread waiting, one thread holding it, then we said, so now there's going to be someone in the kernel, and that's us. Otherwise, now it became free. Right? If it wasn't one, it could have, I guess it could be two already, and then it's, then we should go into the futex wait. Or if it was a one, then we make it two, so now there's someone waiting, so then we go into futex wait. Or maybe it became free in between, because these are not atomic together, it's only one at a time. So now we have to try again. Okay, so now we see, all right, if it's free, set it to someone is waiting. Let me do that. What's going on here? Oh yeah. I don't actually see what's going on here. Should have refreshed on this one. Anyway, it's not entirely obvious clearly how to implement these things. There's always little tricky corner cases that can screw you up. So I think there's a good explanation here. Maybe we should go for it. Go look for that. Let's see. Oh, yeah. Okay, so the reason that there's this intermediate steps is to optimize the fast path. So usually there won't be anyone holding this lock, and or there won't be anyone waiting for it. So it'd be much better if we can just free it without making that system call. So you recall we had a system call doing the futex wait. Here it's only if there is someone waiting that we do the futex wait. But then that adds a lot of extra complication, because now it could be that someone starts waiting just before we do the wake, or just before we check, and so on. All right, I think it's best that we move on. Maybe I'll return to this next time, or maybe I'll post something online. In either case, the general idea here is there's no way for a user space thread to wait without some kernel help. And once we start asking for some kernel help, now it gets really complicated instead. So futex is there to help a little bit. If we didn't have this, oh, I'm waiting for the condition to be so and so, then it'd be really inefficient. So that's what they're doing. Okay, so backing up a little bit, I think all these kernel waits, they have this weird interaction with something called signals. So it's kind of natural to have all of this in one lecture. So a signal, you've probably encountered, let's see, has everyone dealt with signals before in like in systems programming, not in operating systems? Who's done it before? Oh, just a couple. All right, so in that case, why don't we handle that first? So signals are a way to, I don't know how to put this really, without using the word signal. A way to run a little bit of code inside a program in response to some external stimuli. Right? So the most common signal handler is, oh, I receive a signal, any signal, I go kill myself. Right? That's the standard default. That's the default handler for anything. So if I say cat like this, this program will run forever, but it has some signal handlers registered. In fact, let's try it from a distance first. So you can deliver, if you know that's the process ID. Kill, it sounds a little morbid, I suppose, but the kill means deliver a signal. It doesn't mean kill. And there's same thing in XC6. Well, right now there's a function called kill that actually kills the process, I think. But what it should be doing, and which it will be doing in our updated version, is deliver a signal. So if we now deliver a signal, I think the standard one is sig int, I want to say. If I, or maybe sig hup.
You can deliver sig kill, right?
That'll be a -9. Yeah. Anyway, we probably will, maybe we'll find out. So now I say send a signal to this process. We don't know which number signal it is right now, but there's just a number. Okay, we got number 15. So cat got the number 15 delivered one way or another. So how does this work? I mean, cat was running other code, and it wasn't looking for signals. I mean, it was just running its while loop. And really that while loop was a wait, right? So it was sitting in a system call in a wait queue for this input, the pipe probably, or the console input, whatever it is, whatever talks to my keyboard, right, when I'm typing things in. So, so how did it end up writing this thing out suddenly? Because it was cat that wrote this. It's not the kernel that's writing this stuff. So what happened? Well, let's take a look. Let's write a program that does some signal handling. Okay, I'll call this a handler. All right, I think signal handlers should look like this. Should have a void return type. Should accept an integer as argument. I could be wrong. We'll find out. And then, actually, let's ask the man page. Here, signal, this is weird. It should be called like register signal handler. It's not send signal. It's register signal handler. It takes a number and then a function pointer, right? So here's what it looks like, a function pointer. It takes, what the hell is this? It returns a void. It returns nothing, right? And let's see, this goes with that, and this goes with that. Yeah, okay, they say equivalent but easier to read. Let's try that one. Yeah, so this is what I expected, but I don't know what this int here is doing. Could it be a typo? Anyway, so we have the right kind of function. So let's register a signal. Sig int handler. Oh. offsets. Right, so it got upset about this, kind of an aside, but it's still good to know. It got upset about this, right? The SIG int, but it didn't get us upset about that. So this is some symbol that should be replaced by a preprocessor. Right? So the compiler should have replaced it, but it didn't. It left it as a symbol. Then the linker gets to try to deal with it. The linker already linked with the standard, with libc, which has the signal symbol in it, so that's fine. And then it goes and looks for the SIGINT symbol, but there's no such thing in libc. That one should have arrived from signal.h. That's why we got that error. See here, undeclared identifier. So this, actually it looks kind of a little nicer than I would expect. To me, it would have said undefined symbol, really, because it should be the linker doing it. So maybe GCC is, or this is actually a wrapper for Clang. Maybe it's being extra clever and has decided that, this is something other than a symbol. I'm not sure. But either way, this is the problem. I needed to include it just to get the number. I could have said 15 instead. If 15 is the number for, it's term, sig term. Let's do that right.
I don't think you can catch that.
Sure you can. It's sig kill you can't catch. Let's see. Sig term. All right, so I could say sig term here, but there's somewhere up there in the signal.h, there's a pound define sig term 15, right? So it's the exact same thing if I write 15, and then it would compile without signal.h. All right, in either case, let's run this thing. Well, that wasn't very interesting. I think we need a loop. Or I wonder if it'll even allow this. Let's see. Oh. Yeah, okay, it allowed it, but it's kind of nagging. Why is getS unsafe? Buffer overflows, right. So usually you're supposed to pass it a buffer to put the value in, but you don't say how big the buffer is. So getS will put whatever in it and overrun your stack usually. But anyway, we're not even using it, so that's fine. So now if I hit Control C, nothing happens because we weren't handling that signal. But let's try this. What was it? A.out. So kill all just looks for something called A.out and then calls kill on it. So it's the same thing. It's just kind of handy. All right. So there we got a signal 15, but we didn't. We keep running. All right. So kill doesn't mean kill the program, right? It just means deliver the signal. It's up to the signal handler to do whatever it wants with that signal. And that's the case for all signals except for sig kill. So let's try. See what it says. All right, that's fine. So I hit Control C, and now that was our sig int. And we'll try this. That was 15. Try to send a hang up. There's 1, and so on. There's alarm. There's a few different signals. In fact, maybe we should look at the list to see what's there. So ones that we would generally use, sig hup is common. Sig int is the Control C. It's the most common signal, I would say. Most of these are not really something that you would use in daily programming. It's just various errors. sig kill is a force kill. So when you do a force kill on your Mac, try to really kill a program. That's what it is. Send that signal to the process. And what's interesting about this one is it doesn't matter what you try to register. The handler is not called. The OS will just wipe the process. And there's okay. So sig pipe is a special termination. So now you were trying to write to this pipe, but the program after is dead in the pipe. And so now you get a signal saying it's no good. Otherwise, I guess you could have gotten let's see. Yeah, okay, yeah, this is very good actually. So so say you were trying to write to a pipe, but the pipe is full. So it's a blocking write, and it means we end up waiting for the pipe to become available, waiting for someone to read out some of the buffer. So now we're sitting there waiting, and no one's read from the pipe, but the process died instead. So what are we going to do? Well, we have to basically wake up the waiting process, but it's not clear that you can write. And so here we are in that sort of condition wait. It's one of those situations where we were woken up, but the condition is still not true. We still can't write. So in this case, you get a sig pipe message delivered instead of a -1 from the writing. Sig alarm is handy. Maybe you've used this sometime. You can register with alarm. You register like, oh, send me a signal this many seconds into the future, and then you get the signal. That can be good. And see if there's anything else that makes sense. Oh yeah, there's suspend. Not seeing the suspend. Huh. Sig stop. Okay, there's something about that one too. I'm not sure. Okay, so anyway, let's try sending a -9 to this thing. Is it still running? Yeah. What happens if I hit Control Z? Oh, that's good. 18. So Control Z usually should put it in the background, right? The process should suspend. That is, it's not running anymore. It's waiting to be. It's not runnable. It's sleeping, but it can be put back into action with another command. But now we wanted to. Oh, hop. No, 9. Get rid of it. There it is. So the signal 9 is not maskable. It's, I wanted to try that stop too. Interesting. So this one probably isn't dead. This one I think is still running, or still sort of suspended. So if I go, now it came back, and now it's dead for good, I think. Yeah, now it died. Got a couple more signals. All right. So anyway, the idea is it's sort of asynchronously running some other code of mine in the middle of my normal execution. I don't have to be waiting. I can just be printing things out, and then someone delivers a signal, and now suddenly my other code is running for a little bit, and then we're back to running my normal code. So this is some degree of concurrency, right? It's almost like another thread. Like briefly comes in and does something, and then we're back to normal. That should tell us something about what we can do in signals, in signal handlers, and what we can't do in signal handlers, right? It seems very unsafe to modify shared data structures in a signal handler because, well, there's no guarantees what state it would be in when you start modifying. So you can't traverse a linked list because the links could be broken, and Although you could acquire a lock, right? Right, so in the signal handler, we just like grab a lock on the linked list, so now it's going to be atomic and everything's fine.
Well, the process is holding that lock.
Exactly. If the lock is held at the moment, now the signal handler will not finish, and the process certainly isn't going to run because we're in the signal handler, so now we're done. So this is exactly the same situation as in kernel with an interrupt. The signals are very much like interrupts. You can't acquire locks, and you shouldn't be modifying shared data structures unless you have the locks. Yeah. So signals are dangerous in that sense. But how can we deliver these signals? Like, what's going on? Suddenly another thread is running?
Kind of like make a little stack frame on top and then call that function that was given the function pointer from the kernel when it's returning from that key like interrupt.
Very good. So in this case, I guess we had a keyboard interrupt when I hit Control C. That's an easier case to discuss, so let's take that one. So the process is running our little loop. Actually, let's just see it one more time. I hit Control C, right? So it's running that loop. And then when I hit Control C, of course, an interrupt happens. So now it's normal for this process to anyway be interrupted. Like now it's not running that code anymore. It's doing a system call for a little bit. And the only thing that remains is how does the kernel get the program to run a little bit of other code for a moment before going back to its normal execution. So we are used to running other code, but it usually is kernel code. Now we want to be running user code instead. So the user already told us which function they want to run, right? With the sys signal, we register a signal handler. So it ought to be enough to just call that one. Like on return from a system call, instead of going back to where we came from, we go back to this function. Yeah.
Before you call that, you also have to push all the registers on the stack and top them off after the function comes back. So it can have it anywhere.
Well, we had them anyway.
Yeah. But when you go back to user space before you turn to the actual line that it was executing, all the registers are now different from the signal handler.
So the signal handler doesn't really have any expectations on what values will be in the registers, except for the first, for the parameter. So we don't need to worry too much about the signal handler. We just go to it. But we'll have to keep the old state. Yeah. It's not that we need to copy. Well, maybe it might be useful to copy it to somewhere else as a backup. Yeah. Right. Okay, so good. So we set the RIP. Basically, if we see, oh yeah, we're supposed to deliver this signal to the process. Right. In my solution, I had a kind of a signal pending variable. Just say, okay, signal 7 at some point should be delivered to the process. And that's actually the case here. Processes have no reasonable expectation that signals will be arriving immediately. They will arrive the next time you return from a system call or an interrupt.
I figured it would be easier just to wait for the next time we interrupt.
Yeah, or whatever other interrupt happens, right? So next time you switch to this process, and next time you're about to return to user space to that process, you see, oh, is there a signal? If so, we need to do something else.
What happens
So,
if there are multiple signals? So maybe
yeah, there are no guarantees on signal delivery. I think in Linux they keep a small bounded size queue. In our case, we'll certainly only have one. Right? But so, okay, that's pretty good. So now we're setting the RIP to something else. And I guess we have to put in the signal number in RAX so we know which signal got delivered. Was it RAX? No, it's RSI, I think, for the first parameter. Stick that in there, and then back we go to user space. We don't really need to worry about anything else. Let's do it your way. So we just copy the whole trap frame to like let's use this later trap frame. And then we go right back out trap ret. And now the user program is going to run the signal handler. But then what? And then there's a ret.
We need to put the one would be having the return in the kernel itself, and if you save any state, just put that back and then return to the original place the process was executing at.
Let's see. So at the end of the signal handler, what do we do?
You return to the line after that trigger.
Ah, so we should try to go to where we used to be. But this makes for a very complicated signal handler. Because now that one needs to restore all the registers. It needs to get some stuff from the kernel. And it's not even clear that it's not entirely clear that we should be going back to user space. Well, maybe we can. So at least the conventional implementation, I haven't really thought this one through, but it's possible that we could do it all in user space and stay there. Conventional implementation is make another system call. Say, I'm returning from a signal handler, right? Sys signal return, right? So on sys signal return, you see, okay, what was the old trap frame? Copy it in, and then return back to user space. So now we're good.
I was thinking something similar to just injecting, like check when you return from a thread, like having something similar to that.
Yeah, exactly the same thing, right? Yeah, and that's very easy for the OS to do. Just stick a return address at the top. Right. So that's how signals work. There isn't that much to them, and they're really not that powerful. No delivery guarantees, no timing guarantees, and they're very dangerous. And you shouldn't really use them for any sort of critical operations. But they have this handy sort of asynchronous delivery feature, which you couldn't really do a Control-C any other way.
Do all the function pointers get stored somewhere in sysproc? Or just
In the struct proc would be handy, right? Because this is specific to every process. Right? So you would have a little array of signal handlers. So there's some default behaviors. I think it varies. Okay, in Linux, it varies depending on which signal it is. Normally, you would probably kill the process, or that is, the process kills itself, right? Or you would ignore it. If it's not a very important one, maybe it's like the default thing is or whatever. So you can tell, this is called a signal disposition. I think you can tell it like default, and then you can tell it just ignore it, and then you can tell it here's a function pointer. That's what we're going to implement in our homework too. Do the default thing, which is always kill it for us, or just ignore this process, ignore this signal, or run the function. And those are basically the 3 steps in the homework. Yeah, I think that's all I wanted to cover today. Anything else we should discuss? We have a minute.
Why do you think the process actually stopped when you sent it the other, when you sent it the stop from the other window?
When I sent it a sig stop, yeah. I don't know what's happening there. In fact, I'm a little unclear on what a sig stop is supposed to be. Here. Instructs it to stop it for later resumption. Huh. So that's what happened, right? But why did it die? So what's signal 19 and 21, and then it's just not doing it anymore.
Control-Z, what's that doing?
Yeah, I thought that's sig stop.
Well, I can say, what if you
It doesn't do it. Yeah, it does. It gives us a different number. Oh, 18.
Yeah, so that's 18 versus 19, you said.
generated from keyboard. Another stop. Yeah, but okay. And then there was the continue. That's good. So just to notify you of what's going on, I suppose. And that was 21. Yeah. Background read attempted from control terminal. Aha. All right. So. All right. So if we don't do a read, now it's not going to die. So I think the problem was we were trying to read when we were in the background, then we don't actually have access to the terminal. That's probably the problem. Let's see. Control Z. Stop. Foreground. Ha. Cool. Good question. All right. That's it. I'll see you Thursday. Good luck with the rest of the homework.